Hello, this is Calculus Lesson 3.12, and today we're starting antiderivatives. So go ahead and try your warm-up. Number 1 is Newton's method, and number 2 is finding the equation of the tangent line. Okay, so number 1, we want to find where these two graphs intersect each other. So wherever they intersect is where they're equal, so that's what we want to do first, is go ahead and set them equal. And then it would make sense for me to multiply by x so that I can get rid of that 1 over x. So I get x cubed, x plus 1 equals 1. Go ahead and distribute x to the 4th plus x cubed, and we'll minus the 1 over. Okay, so this is my equation, and I want to go ahead and set up my Newton's method equation. So I have xn plus 1 equals x sub n minus, we have our original on the top, and on the bottom we have the derivative. Okay, so you could have started with any guess. Just from looking at this graph right here, my first guess I used as 0.8 because it just looked like about 0.8 to me, but it doesn't matter what guess you start with because Newton's method will hone you in on the correct answer. And the only difference with different guesses would be the further off from the actual answer you are, the longer it's going to take you to get to the right answer, the more x sub n's you're going to go through. All right, so let me set up my chart here. So I have n, x sub n plus 1. Okay, so I have my first guess, n sub 0. I said I was going to use 0.8. And I go ahead and plug 0.8 into this equation, and I get 0.819758. 0.645. I'm going to just stop it there. So that is my x sub 1. Okay. And now I plug that in to my equation again. So the second time I did it, I got 0.8191730407. So that's my x sub 2. Okay, and then I go ahead and plug that in, and the third time here I got 8191725,134. And so since I had to do this correct to 4 decimal places, I'm noticing that now I have not only 4 but 5 decimal places repeating, so I'm going to go ahead and stop. So my answer to accurate to 4 decimal places would be, rounding it correctly, 8192. So again, if your first guess, let's say you started with a guess of 1, okay, it might have taken you a little more steps to get to the answer, but we should all arrive at the same answer eventually. So I don't want you erasing your work if you had started with a different guess. As long as you were winding up with the right answer, you can go ahead and keep that. All right, number 2, find the equation of the line that is tangent to the curve x squared plus 2y squared equals 9 at the point 1, 2. Okay, so remember the first thing we want to do is find our slope of our tangent at that point, and to do that we take our derivative. You probably noticed that the y is kind of mixed into this whole equation, which means we're going to do our derivative implicitly. Okay, so we start from the left, we have 2x plus 4y dy dx, since I did the derivative of the y, equals 0. All right, so now I'm just going to isolate my dy dx, so I'm going to minus the 2x, and then I'm going to divide by the 4y. Okay, so that is my slope. So my slope of my tangent is negative 2x over 4y. I now want to plug in my point, my x and my y. So my slope at that point is going to be negative 2 times 1 over 4 times 2, which is negative 2 over 8, or negative 1/4. Okay, my last step now that I have my m is to find my b. Okay, so I'm just going to erase some things over here. Hold on. Okay, so I'm going to use my point and I'm going to plug it into y equals mx plus b and solve for b. So 2 equals negative 1/4 times 1 plus b. Add the 1/4. So my final answer is y equals negative 1/4 x plus 2 and 1/4. All right. So today we are starting antiderivatives. So let's read the definition here at the top. A function capital F is an antiderivative of lowercase f on an interval I if the derivative of capital F is equal to lowercase f of x. Okay, so basically what we're doing is we're trying to find functions that if I took their derivative, I would wind up with the function that I am given. Okay, so basically I'm going backwards. Okay, so let's look at example 1a. These are very simple antiderivatives, so we're just getting your mind kind of thinking about how this is working. So if I'm looking at a, I want to think, what would my original function have been if when I took the derivative of it, I got 2x? Okay, so we denote this as capital F. Okay, and clearly the original function would be x squared because when I would do the derivative of that, I would get 2x. Okay, and then also don't forget that there could have been a constant on the end of this that when I took the derivative, it disappeared. So we want to add that constant, just acknowledging that there might have been another number there that disappeared when we took the derivative. All right, let's go to B. So now I'm thinking what has cosine as its derivative, and clearly we know that's going to be sine. Derivative of sine is cosine. And then I want the plus c for the constant that might have been there. All right, let's go to C. This one got a little bit trickier. So the first one, what has 1 over x as its derivative? So hopefully you're remembering that 1 over x is the derivative of the natural log of x. And that is one that you do have to know, okay? There's no figuring that one out. You have to remember that. And then the second part here, we have e to the 2x. Okay, so remember, I know that whenever I have an e, the derivative is the same, right? The same as the original. But when I do the derivative, I do the derivative of the top, the exponent, and that goes down in front. So the derivative of 2x would be 2, which is what I have in my equation. So that means I'm done here. Okay, I don't need any number in front, but I do need my plus c. All right, theorem. If f is an antiderivative of f on interval I, then the most general antiderivative of f on I is capital F of x plus c, where c is an arbitrary constant. All right, let's look at example 2. Find the antiderivative of 3x squared. And then on this one, they actually gave us a little bit more information. They're telling us that f of 1 equals negative 1. So they're actually giving us a point for xy that we can go ahead and plug in to solve for c. All right, so let's go ahead and do this. So we have f of x equals, what has 3x squared as its derivative? That would be x cubed plus c. I'm going to go ahead and plug in my x and my y minus the 1, and now I know what my c value is. Okay, so these examples are ones that you can look at, and just using your knowledge of derivatives that we've already done, you can just kind of figure them out. But we definitely want to have a little bit more technique and structure so that if there was a difficult example that wasn't obvious to us, we would be able to figure it out. So let's look at the next page. And what I have here are I have formulas for all your antiderivatives. So just for a basic power function, like a polynomial, what you're going to do is you're going to add 1 to the exponent. Okay, that makes sense because when we do the derivative, we always minus 1, right? So we're going to add 1 to the exponent. We're also going to divide by whatever number we put as our new exponent. And the reason for that is when you do a derivative, you multiply by the exponent. So we're kind of undoing that part. Okay. We also have the antiderivative of sine. Notice here I have kx. That just accounts for maybe it's not going to be a regular plain sine of x. Maybe it'll be a sine of 2x, okay? And if that happens, you want to make sure that you are dividing by that letter k. Notice for sine, you're getting a negative cosine because remember, derivative of cosine is negative sine. So you have to balance that negative there. Okay, we have cosine, secant squared, cosecant squared, secant tan. These are all things that we knew were derivatives. And now we're naming them as antiderivatives. Another good one to look at is the e one. Okay, you're keeping your e to the kx, but you are dividing by that k, okay, to counteract. 1 over x is natural log x that we talked about. And then here we have some of those inverse trig functions that we had formulas for. Oops, I went too far. So those are just good to remember that you do have formulas for those. So you might see some of those and they're going to look like a little bit crazy and you're going to think, I don't know how to do this. Well, they might be an inverse trig function. Look at your formulas. And then the last one is a to the kx, and that is, again, a formula. And we'll try one of those on F down here. All right, let's try some examples. Okay, so number 3a. So remember what we're going to do to find our antiderivative. First thing we're going to do, we're going to add 1 to the exponent. Then we are going to put 1 over that number as a coefficient. What that does is it will cancel with the 6 when the 6 comes down front to take the derivative. All right, let's go to B. On B, it is very, very wise for you to rewrite this function first. And how do I want to rewrite it? As an exponent. Okay, so I want to rewrite this as -1/2. Okay, all right, now I'm finding my antiderivative, so I'm adding 1 to the -1/2. So that would be a +1/2. And then I am putting 1 over that new exponent in front. Okay, so 1 over 1/2, that's just 2. Okay, let's go to C. We have sine of 2x. Okay, so my antiderivative, I would have cosine 2x. And then out front, I want to do a -1 over my coefficient, so -1/2 out front. Okay, letter D. Remember when you have x over 2, that's really a 1/2 x. Okay, so remember that. So on this one, our coefficient is actually 1/2. Okay, so we have our antiderivative. It's going to be a sine of x over 2, or 1/2 x. And then out front as my coefficient, I want 1 over 1/2, which is 2. All right, let's go to E. So remember for E functions, we're going to keep that the same, but we do want to have 1 over k out front. So that would be -1/3. All right, and then our last one, F. This is this special one here. It's just a formula. So you just want to focus and plug in everything to the formula. So remember on this one, our A is 2 and our K is 1. There is no coefficient other than 1 on this one. All right, so we have capital K of X, my antiderivative. It's going to be 1 over the natural log of 2 times 2 to the x. All right. So pretty simple lesson today. You have for homework 10 examples like this. And remember just to use that formula sheet that I just gave you and just do your best. One thing I'm noticing that I just want to point out, like on number 1 and number 2, they have these coefficients on them already. Okay, we didn't really do one like that. So let me just show you one like that before I let you go. So I'll give you one more example from your notes. Okay, let's just do another example. We'll make it, let's see, what was this one? 2x to the 5th. Okay, let's do 5x to the 4th. And no, I'll make it 3rd. Okay. So when you do your antiderivative here, I just want to show you what happens when you have a 5 in front. So you're still going to add 1 to the 3. That's going to become a 4. You're going to divide by 4 out front, and then the 5 just stays on the top. Okay, so like on this one where we had 1/6, that was because there was an invisible 1 in front of the x to the 5th, right? So when you have a 5, it just goes on the top instead of the 1. Okay, all right. So go ahead and try those and let me know if you have any questions.